Okay, so last time we stated the inclusion-exclusion principle for probability of a union. So it's just equal to the sum of the probabilities, and then I subtract off the sum of the probabilities of each event, and then I subtract off the sum of all the probabilities of all the intersections of two events, and then I add in the probabilities of all the intersections of three, etc., and I proceed in that way. Here's an example with, in the case you would like a more readable example. If I have three events like this, first I just add all their probabilities up, but then I subtract off all the doubles, but then I have to add in the triple. If I had four, I would have more terms, right? I'd have four terms here, and then I would have to subtract off all the doubles, add in all the triples, and then finally subtract the last intersection of all of them. Okay, so here's the method for the proof. We're going to let S be some arbitrary outcome that's in the union of the EIs. So it's in at least one of the events, okay? And we're not going to make any other restrictions on S. It's just in one, it's in the union. It's an outcome in the union. It could be in one, it could be in all of the events. It could be in some of the events. And we'll suppose, because we're going to need this to do the proof, we're going to suppose it's in exactly M of the N events. So, and then M is also arbitrary. So it might be in one, it might be in all N. M could be 1 through N, in other words. But it might be, N minus 20 or something. You don't know. So M is just some number between 1 and N inclusive. Okay. And it just counts the number of the events that S is contained in. So what I'm going to do then is show that P of S is contributes once to the left-hand side. Actually, that should be clear because the probability of the union is the sum of the probability of the outcomes that are contained in the union because they're mutually exclusive. So I tried to make a little picture of this. I don't know if you like the picture, but yeah, so here's a picture of the sample space, big S. Here's my little s that I'm going to do the proof with. And here's other s's in here, S7, S99 maybe. There's all these other outcomes in here, S12, S50. Okay, others, maybe really tiny little ones. This is the one I want. So now I have events. Events are collections of outcomes, right? And they can overlap. And I just want to say that this S is in M of the N events, okay? So S is in M of the N events. Now, the probability of the union of the EI is just equal to the sum of the probabilities, okay? Here is the union over here. So this is the union. And this is the complement of the union over here. We don't need this, okay? So not in. All right, so how do I show? So it's counted once here. So the strategy is, does it say it? So S is an outcome contained in exactly M of the N events. S is counted one time in the union. Okay, that's right. So we just want to show, so the goal, show S is counted net once on the left-hand side. Okay, so look, we know if it's in M of the events, say M is 10, it's going to be counted 10 times in this term. But the thing is, it will get subtracted out over here. So the idea is a net of one time on the right-hand side. And when I say S is counted, I mean P of S is added in at a net time of one time. So it's added in, but then it's subtracted out, added in, and we just want to count the net time. So we're going to count each term. All right, so you're going to help us. So we have P of S, or you can just write S, is counted M times, remember it's in M events, in the first term. Okay. Now what about the second term? Also, S is counted, I'll leave it blank, in the summation here. Now here I gotta write the summation a little more carefully. I1, I2 less than or equal to n, greater than or equal to 1. Okay, all the doubles that are possible, that's what this says. Pick any two indices in here such that they're not the same, and this will give me my. So how many possible pairs are there where S is counted in both? Well, it's in M of them, so I can choose any two of those M. So S is counted M choose 2 times in this. This has a total of N choose 2 terms, but notice that S will not be in those intersections where there's at least one event that doesn't include it. All right, continuing in this way, we have S is counted M choose R times in sums of intersections of size R, right? If I want 3, then I have to see how many ways I can get 3 of the M events that contain S. Also, let's keep it. Also, S is not counted at all in intersections and sums of intersections of more than M events. Because clearly, if it's only in, say, 3 events and I have an intersection of 4, then I'm including an event that doesn't contain S. So that ruins the whole thing and it's not counted. Okay, so we're in good shape here. We've got counts for it on the left, on the right, on the I should have wrote right-hand side, right? Here, this should say on the right-hand side. Okay, so we've got counts for each term, and we know the signs, so we just have to add it together, okay? So let's do that. So on RHS, S is counted. Okay, let's see, M times for the first term. So let's see, can I, yeah, look, I can show you here. It's counted M times there. Now, if I go down to this term, it's M choose 2, right? But that's minus. So it's counted M minus M choose 2, and now plus M choose 3, and now minus, and dot, 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 all the way up until I get to the mth one, which would be minus 1. It just alternates, M plus 1, right? Because if it's even, the sign is negative. And this would just be 1, right? But I'll write it M choose M here just to be clear. And then it stops. And in fact, let's be super clear and put m choose 1 there, even though I don't think of it that way. I don't think of it that way, yeah. But okay, so we have this. So I have to show you that this is the number 1. Okay, well, I think the binomial theorem will work here, right? We'll do just fine here. So if I call this, let's try to use the binomial theorem here. So I'm going to say this is equal to, let me add in a negative m choose 0. This is going to be m1 minus dot 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 minus 1 to the m plus 1 m choose m. Now what's m choose 0? M choose 0 is 1. So I added a minus 1, so I have to also add a plus 1, right? You can't. You've got to keep the equal sign, the integrity of the equal sign there. So I added a minus 1, I add a plus 1. Now let me factor out a negative sign here. So this is equal to minus m choose 0 minus m choose 1 plus dot 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 plus, this becomes minus 1. This sign switched, so I could write m here now. M choose m. And still plus 1, right? Okay, but what is this in here? This is just the binomial theorem unrolled backwards, right? K equals 0 to m choose k, and it just alternates between 1 and minus 1. So at 0, so let's see, I think the safest way to do it is minus 1. So I want it positive now. I'm not counting this minus sign. So I'm going to have minus 1 to the k and plus 1? Yeah, plus 1 to the m minus k. This will do it, right? This will give me this. So this whole thing is equal to minus this plus 1. All right, but what's the binomial theorem says? This is equal to minus 1 plus 1 to the m plus 1, which is just equal to 1, right? 0 plus 1. Okay, so that's the proof.